I'm going to give you a short overview of the LCD products that we have in our portfolio, a little idea about the Cortex-M3 products. So just a quick agenda for you. So I'll do the introduction. Dave will go over the LCD terminology, about the interface and signals, some system issues, so some actual design issues to consider. We'll talk about software and tools, and then some of the support things as well. So we have Q&A listed at the end, but please don't wait to the end. If you have any questions, just interrupt right at the beginning. Okay. LPC1788. This is our newest Cortex-M3 device. It's with LCD, external memory bus, a lot of on-chip flash, a lot of on-chip SRAM, and I'll get into some of the details on that. But first, a quick overview. I won't spend a lot of time, a lot of marketing stuff on this, but just in general, if you're not familiar with NXP and ARM, we're the very first company to do ARM microcontrollers with embedded flash. We did that back in 2003. And we've done hundreds of ARM devices, and we actually ship more ARM microcontrollers than anybody in the world. That's ARM 7, ARM 9, Cortex-M3, Cortex-M0, Cortex-M4, all combined, we ship more ARM than anybody in the world. Sorry. We offer PIN and software compatible solutions. We offer what we call bridges. So between an ARM 7 and an M3, we have a PIN compatible version. If you're using the ARM 7, you want to switch over to the M3, we have that. Between M0 and M3, can't decide which is the right one, PIN compatible version between M0 and M3. Between M3 and M4, also PIN compatible. So the exact parts, just take out one core and put in the other. So if you're not sure which one you want to do, you have some higher end applications, you can use the same board and just swap parts in and out. We try to make it very flexible, as well as using the same IP through some of these different parts so that you can migrate your code up and down from M0 all the way up to M4. And we also try to offer you choice. So we're the only company right now in the world that's currently shipping M0, M3, and M4. There have been some other guys who made some announcements, but we're the only ones actually shipping those devices. Focusing a little bit more on the Cortex-Ms, we're ranging from 65 cents. These are 10K prices, by the way, 10K through distribution. So if you were to go to Arrow, Avnet, Future, Mazar, DigiKey, and get 10K pricing, this is the suggested resale price for that through them. So starting at 65 cents for a 32-bit controller, all the way up to $7 for a Cortex-M4 dual core, so it's an M0 and M4 LCD controller, external bus, 1 meg of flash. You get a lot of stuff up to 200K of SRAM, a lot on that for $7. And then we have the M3 that kind of spans in between both. NXP has really differentiated ourselves with performance, with peripherals. We have a lot of nice new configurable peripherals that are proprietary to NXP. Something we call a quad SPI flash interface that allows you to look at quad SPI flash or regular SPI flash, and it appears in the memory map of the device. We have some API handlers that will allow you to do some very configurable things so you don't need to engage the CPU. And we also have some other things that we call serial GPI that will allow you to do some customized waveforms. These are all very customizable. They allow you to do whatever you want. We have some examples, but there's a lot of things you can come up with based on these things, and they're proprietary to NXP. These are the types of things we've done. That's how we've gotten the leadership in the ARM microcontroller and how we're trying to maintain it. So I mentioned the bridges earlier. So specifically, if you've used any of these ARM 7 devices, 24.3x, 4x, 6x, 24.5x, 23.80x, or 24.7x, we offer PIN-compatible versions to each of those. So if you've been an ARM 7 customer of ours in the past, you want to switch over to M3, we make it very, very easy for you. And yes, that is the Zachem bridge. No, yeah. 23.7 actually is part of that. I put 8x, but 7x is there as well. Yeah. Yeah. Okay, so what is the LPC1788X? Cortex-M3 operating at 120 megahertz. It's got all the, when ARM offers some a core, they give you a few optional blocks. We include all those. So we offer the memory protection unit. The NVIC everybody includes. It's in there, the full debug and trace serial wire debug and the full JTAG debug. Has up to 0.5 meg of on-chip flash that operates up to 120 megahertz. So you can operate near SRAM speeds with the flash, and we do that with some proprietary flash memory controller. Up to 4K of true double EEPROM, so that's one million cycle erase. So you can use that for serialization or other customization stuff that you may want and not have to use the flash. and up to 96K of SRAM broken up into multiple blocks so that you can have your USB looking at one block, your core looking at another block, your Ethernet looking at another block, and they can all operate simultaneously without bottlenecks. We now have a USART, so synchronous UART, in addition to the other 4 UARTs that are on the chip, so a total of 5. And it also has a smart card interface. And we have a new thing we call an event recorder. This is in the real-time clock domain, and basically if it gives you 3 inputs from external devices, and it'll register anytime you have activity on that line. So for example, if you want to have, we developed for a metering customer, they wanted to know if somebody lifted up a lid, it would flip a switch and toggle that pin. So this would give you a timestamp exactly when that happened. It operates in the real-time clock domain, so it's very low power. So they use it for tamper detect, but I could think of other applications. We've had some vending machine guys that have had some interest in a suntan bed guy that have had some interest in that. So there's a lot of different things you can do, but since it operates in the real-time clock domain, you can power off the rest of the chip and just keep that portion running. And then what we're going to talk about, it has an external memory bus, USB, Ethernet, that's full-speed USB on-the-go host and device. And then what we're going to spend all the time, Dave, talking today is the LCD controller. And this is a true full LCD graphics controller, not some display or not some little segment driver or something like that. So 4 parts in the family specifically that support it are the 1788, the 1787, the 1786, and the 1785. Now you may say that's a lot more than 4. Those are different package variations that we offer with each of those devices. So you can see we offer a 208 pin. The number at the end is number of pins. A BGA 180 or 208 pin BGA or LQFP, 144 pin LQFP, and those are our LQFP 208s. So we give you some different pin compatible options up and down, and the main variations are the amount of flash and the amount of SRAM on each of these, and then whether it has Ethernet or not. These are all available on our line card or online. And then the last slide that I'm going to show you before we show you a quick demo of this is we now have gotten into a deal with Sager to offer their very, very popular MWin library for free. So as long as you use it with our microcontrollers, it's free, totally license free. So operates with any ARM controller we have, including but not limited to these devices. These are all families that have LCD controllers with them. But if you have an LCD controller that has the built-in frame buffers, you can use any microcontroller we have, including our M0s. So it supports monochrome, grayscale, or color LCD, configurable display sizes, compile time switches. You can develop this outside of your application code, so you can give it to one person to do the GUI and have someone else do your application code. And then you also virtual display, so if it's larger than the actual display, you can do that as well.
So the first thing I'm going to talk about is LCD terminologies and technologies. So one of the things when you're first getting into LCD, the first thing you have to understand is some of the vocabulary words for the technology. So the first thing I'm going to mention is resolution. Some people are concerned with the size of their display, but when you're designing something with an LCD, you're more concerned with the resolution of it. So some popular resolutions are QVGA, which is 320 by 240, VGA, which is 640 by 480, and SVGA, which is 800 by 600. You might be familiar with some of these from the PC world. PCs they used to use SVGA and also XGA. Another important thing to keep in mind besides resolution is the color depth or bits per pixel. So this is actually an example of how the data is organized in memory. So in this particular example, what we're showing is 16 bits per pixel. And there's 5 bits of red, 5 bits of green, and 5 bits of blue, plus a bit that's not used in this particular organization. So does everybody know what a frame buffer is? A lot of people are shaking their heads, so I'll try to speed this up. But a frame buffer is a contiguous memory buffer containing a complete frame of memory. So what the frame buffer has in it is it has the color values for every pixel on the screen. So for a QVGA display, which has 320 by 240 or 240 by 320 pixels, there's actually 2 bytes per pixel if you use 16 bits per pixel, that equals 150 kbytes of RAM. So that's the size your frame buffer needs to be. The frame buffer is sent to the LCD panel a certain number of times per second. It depends on the refresh rate of your display, and that causes a lot of bandwidth in the system. So the two important things to figure out the size of the frame buffer are the resolution and then also the bits per pixel. So the bits per pixel, or the determines the amount of color that is on your display. And common values are 1 bit per pixel for a monochrome display. This means you can have actually 8 pixels represented in a single byte in the frame buffer. You can also have a palette-based display, which if you have 2 bits per pixel, that's probably the smallest palette-based display that you can have. That gives you 4 colors. Moving up from there, you can have 4 bits per pixel and get 16 colors, 8 bits per pixel and get 256 colors. So moving on from the palette-based displays, you can move on to high color or true color. High color is 16 bits per pixel, and so that allows you to choose pretty much whatever color you want for the display for any pixel. On 24-bit, this is similar to 16-bit, except it takes 3 bytes per pixel, and you get more color resolution. You get 8 bits per color channel instead of 5 bits. So some of the resolutions, some of the bits per pixel levels I mentioned are palette-based. So what this means is that in the frame buffer, you have these numbers and they index into a color palette. And the color palette has programmed into it certain colors for each palette value. And then as the image is sent out to the display, the color palette entries are converted into the actual RGB values that are written to the display. So the LCD controller that's in the LPC1788 and all of the other NXP microcontrollers that support graphical LCDs have up to 256 palette entries. So this means that if you don't want to do high color and you don't want to do true color and you're trying to economize your frame buffer size, then the maximum number of colors you can have is 256. So when you do a display with 256 colors, you get to choose in advance what the colors are, and then for each pixel you can select one of those colors from the palette. So there's 2 main LCD technologies these days. There's the 2 main graphic LCD technologies. There's the STN, which is a super twisted pneumatic, and the TFT thin film transistor. So we're starting to see a lot fewer STN displays. It seems like the market is really switching over to TFT, but if you do a monochrome display, perhaps you'll still use STN. So the response time of an STN display is a little bit less than of a TFT display, but the cost and power are usually less as well. There are color STN displays, and there's also our controller will support a dual STN display if you want to have 2 displays. So the STN displays only turn the segments on and off, whereas TFT displays give you more flexibility in that you can actually get gradations of color for each pixel. TFT have a very fast response, but they use more power and cost more than STN. Some variations of TFT displays include AD TFT, as well as advanced TFT, as well as a highly reflective TFT, which you can read outdoors in the sunlight. This shows an example of an STN display, which is clocked from our controller. So on the STN display, there's a single pixel is made up of 3 RGB elements. When the data is clocked out to the display, you actually clock it out. You typically, with a 4-bit display, a clock of data will drive 4 elements, or 1 1/3 pixels. So do you see that? This is actually a 4-bit display, so it's actually going to drive 2 reds, a green, and a blue out with a single clock. So what that means is that an entire line of 320 pixels can be clocked out in 240 clocks. So this is a little bit different from a TFT. So TFT, on the other hand, what you typically do is you have the pixels are arranged as RGB blocks. And then every time you clock out a pixel out to the display, it's 1 clock per 1 pixel. So this will take 320 clocks to clock out the data for a 320 pixel wide line. So let's look at the signals that are used to interface to a TFT display. So the main signals are the VSync and frame pulse. So if you're using an STN, you call it frame pulse. And if you're using a TFT display, you refer to it as VSync. What the VSync signal does is when the display scans all the way to the bottom, you send the VSync to tell the display that you're going to start sending a new frame of data. And the next signal that's important is HSync, or also known as line pulse. So again, with the STN, it's called line pulse. With the TFT, it's called HSync. What that's done is when you scan across the display, when you reach the end or the beginning of a line, you send a line pulse. One of the most important signals is the pixel clock. So every time you're going to send data to the display, you have to send out the pixel clock. Our controller allows you to supply an external pixel clock, but most people will generate it inside of the part. There's a divider, and you can divide down the CPU clock and create the pixel clock that you need. And then finally, we're down to the data lines. So the data lines, it's just the data, the digital data that is sent to the display. So really, when you think about it, a graphic LCD display interface is very, very simple. It's actually, the timing for it is much simpler and easier to understand than a segmented LCD display. Because typically on a graphics LCD display, the display driver is on the display. And so you just need to send digital data to it to display the image. But it's not easy to send the digital data because you have to constantly refresh it. And that's what our display controller does for you. So one of the things about the vertical sync and the horizontal sync, when you reach the end of a line, there's actually a little bit of extra data before you wrap around to the beginning of the next line. And that's known as the back porch. And then the data after the sync before the next line is called the front porch. So I'll talk about that a little bit. That timing comes from the LCD data sheet, and you put it into our controller, and then it drives the display for you. One key number to keep in mind, this is actually kind of a big deal, is the refresh rate. So what the refresh rate is it's the number of times that the display is updated every second. So as an example, to calculate the refresh rate, if you have, so the pixel clock is specified in the LCD data sheet. So when you select an LCD, you say, oh, I want this 7-inch LCD and it's this resolution. If you look in the data sheet, it'll have a specific pixel clock. So in our example, we're using a 6.5 megahertz pixel clock. The pixel clock is how fast the pixels are sent to the display. So if you divide out the vertical resolution, the front porch, the back porch, the pixel clocks per data line, and then the horizontal front porch and back porch, then you will arrive at the refresh rate, which is the number of full frames that are sent every second. So typically 60 is a common number, and so anything you get should be near there. So like it probably won't be less than 60, and it shouldn't be too high, like higher than 80, because it's just wasting bandwidth in your system. The largest configuration for the 1788 LCD controller uses 31 pins. But if you're using an STN panel and it's monochrome, you could use as few as 10 pins. So this is one of the reasons, if you look at the chart that lists all of the parts that have the LCD controller, they tend to be parts with the higher pin count. Because first of all, as I mentioned, you need to have a frame buffer, which is a contiguous block of memory. That's usually a larger block that is put into SD-RAM. This is not by any means a requirement, but in most people's system design, the display frame buffer is so large they need to add SD-RAM. So the parts that we offer that have the LCD controller also have the SDRAM controller on board, and that is pinned out in the package. Then the LCD controller uses a separate set of pins to go to the LCD panel. So because the largest TFT full color configuration can use 31 pins, and then you also have to add the SDRAM controller pinning to that creates a need for larger packages for LCD parts. So this actually shows how many pins are used for several different configurations for STN. So for a 4-bit monochrome STN, this is an STN that shows like you might have seen these. They're displays that it's like gray and blue, and it'll show different darknesses of blue, or they can also be different shades of gray. So that's typically the 10-pin configuration. And then you can go all the way up to a color STN at 14 pins. For TFT, these are much more common today than STN. Probably the most popular configuration I have seen is the 565 RGB. So that's 5 bits of red, 6 bits of green, and then 5 bits of blue color information, and that'll take up 22 pins. So this is actually the diagram I mentioned before, where we have the front porch and back porch timing. So what happens is, as the LCD, the data is sent to the LCD, at the beginning of each frame, there is a VSync pulse. Then there's a period where nothing is sent to the LCD. This is called the back porch, and this is inside the LCD, the display driver chip. It's busy preparing to drive the LCD. What it is doing, it kind of depends on the design of the display driver chip. And we don't really know, but in the data sheet for the LCD panel, it'll specify, there's a vertical back porch timing of 6 clocks or so many microseconds, and you got to put that into the display controller. And then in the beginning of each line, there's a front porch and then a back porch. Those are the same things as part of the display driver timing that you'll find in the LCD data sheet. So put those in, you'll be fine. And then there's also a vertical back porch. So here's an example of an LCD datasheet. This is a truly display. It's 240 by 320. This one's actually programmable. So we set it up for landscape, but you can actually program this one to be portrait as well. So it has in here is the LCD clock frequency. It says typical is 5.5 megahertz, maximum is 8.22 megahertz. So does anyone want to guess what happens if you go to too small of a value? Because it doesn't have a minimum, so what is the restriction? Anybody know? What? Yes, it flickers. If you see your display flickering, then you should use a faster dot clock. So anyway, so they specify 5.5 as a typical average value, and try that. And if it flickers, then you could try 7 megahertz, because 8.22 is the max that's specified. So anyway, so there's all these different characteristics. Like there's also the horizontal back porch, which is 30 dot clocks. Horizontal front porch is 10 dot clocks. So using this information, you can put together the parameters necessary to program the LCD controller in the LPC1788. This is an example of what happens if you get some of the parameters wrong. It's not a catastrophic failure usually, but not for these anyway. But like this, what happens here is we put in 8 for the vertical back porch instead of 4 like is in the data sheet. And so we just end up with a little, the whole image is shifted over, and there's wasted space up here. So, I mean, if you guys start to use this LCD controller with a lot of different displays, I mean, usually any problems you find are pretty easy to correct. So here's actually showing the horizontal timing. So one of the things to keep in mind is that the data phase is, sorry, this is the panel data. The panel data is only active outside of the back porch and front porch regions. And this is the vertical timing. So what this is showing is, here's the vertical sync pulse, and then here's the back porch, and then here it sends all the horizontal lines, and then here's the front porch. So this is pretty much what I described before. So now let's talk a little bit about the NXP microcontroller products that actually have the LCD on board. So, or some of the features, in other words. So the LCD controller that NXP offers on the LPC1788 is supports up to 1024 by 768 resolution, and it supports a color depth of up to 24 bits per pixel, which allows 16 million colors at the same time. You can also use a palletized display with up to 256 colors. So what that can do is that can really reduce your bandwidth and allow you to support larger displays without as much system utilization of the SD-RAM. So the bus size can be configured to the LCD. So if you have a RGB565 LCD, you can shrink it from 24-bit data to the LCD down to 16-bit data to the LCD. So this allows you to easily use different panels without having to use up all the chips on the part. There's a dedicated DMA controller for the LCD. So one of the things with the LCD is that the frame buffer has to be output to the display over and over 60 times or 70 times a second. And we have a dedicated DMA that takes care of that. So once it's set up, it just runs in the background. The same LCD controller is present on the LPC1850, which is a Cortex-M3 product, the 4300, which is Cortex-M4, the 3255X, which is a ARM9 product, and the 247X, which is ARM7, and then as well as the LH7 devices. So this helps reduce software porting efforts, and is one of the reasons why there's so many LCD toolkits that are available for our parts. So to configure this LCD controller, the first thing you have to do on the 1788 is in the PCON P register, you set the PC LCD bit. So people who are familiar with the 1788 or with other NXP parts might be familiar with the PCON register. Basically, there's a bit for every peripheral, and you have to set the bit in order to turn the peripheral on. So you set this bit, but one other thing you have to keep in mind is LCDs sometimes have a power-up sequence, so check the data sheet. Like maybe you want to turn on the clocks before you power it up, or maybe you want to power it up before you turn the clocks on. It kind of depends on the LCD. On the 1788 LCD controller, you set up the clocks and timing registers following the power-up sequence of the LCD. And then you, actually this should go first. You can set up the pin and pin modes in the IOCON registers. So basically every pin on the 1788 has an IOCON register where you specify what function it is. So it can be GPIO, or it could be part of the LCD controller, or maybe it has some other function. So it's important to set up for all the LCD pins. Oh, these are all going to be the LCD controller data output pins. And this is going to be the clock for the LCD controller. This is actually a diagram showing the Dual-CSTN data flow. There's a lot of extra stuff in the chip to support the STN displays. So if you're able to take advantage of the cost savings and the power savings of an STN display, I would say go for it. But for instance, one of the things that's in STN that's not in TFT is a grayscaler. And then if you look at the TFT data flow, it just pretty much reads data from memory and then outputs it to the display. One of the things to keep in mind when you're developing a system that uses a LCD, graphics LCD, is bandwidth. So I mentioned the frame buffer is a certain size depending on the resolution and then also the number of bits per pixel. So typically with a QVGA display, you might have 150K frame buffer, and then that'll get transmitted out to the LCD perhaps 70 times per second. So that creates a bandwidth load on the SDRAM controller in the system. So we have a bandwidth calculator where you can put in the clock speed that your memory is running at, the bus width for the memory. So depending on the package that you get, you could end up with an 8-bit or 16-bit or 32-bit SDRAM controller, or maybe in your system design you're trying to economize, so you might decide, oh, I'm just going to use 16-bit SDRAM if I can, and I don't want to use 32-bit SDRAM. So in that case, you can use a bandwidth controller to check out whether that's a good system. So you put in here the bus width for SDRAM and the speed of the bus, also the LCD size, and then the refresh rate that you're going after. So I mentioned the refresh rate's typically around 60, but it could be 70. And then when you're done, you'll come out with a bandwidth utilization. So in this particular example, this is a 640 by 480 display. And it's using 16 bits per pixel. So it comes out to 43% of the bandwidth of the external memory controller. So depending on what kind of display design you use, maybe a larger display would use less bandwidth if it was fewer bits per pixel, but you can figure it out before you build the system. This is what happens if you don't have enough bandwidth. You will see tearing on the LCD display. So actually, to simulate that in this system, what we did was we took the LCD bandwidth and we raised it up artificially to 50 megahertz, just so that we could take a picture of this. But this happens because the LCD DMA is unable to service the LCD FIFO in time. This isn't always so obvious. We set it to 50 megahertz when it's normally 6.5. If you want to find subtly if you're ever missing LCD FIFOs, then there's actually an interrupt you can turn on called the LCD underflow interrupt, and then you can find out if there's ever a time when the FIFO runs out of data, which you don't want to happen because it'll usually cause some sort of visual thing, but usually much smaller than this. So again, workarounds for this are you can use a lower refresh rate on the display. Make sure you're using 32-bit external memory. You can use faster SDRAM clock speed. Although on the 1788, the fastest the external memory controller will run is 80 megahertz, but there's other products like the LPC1850 or the 4350 where the external memory controller will run at 120 megahertz. So again, it's kind of a system design thing. You have to make sure you have enough bandwidth for the size display and the color depth and everything that you choose. You could just maybe a solution to this might be using 16 bits per pixel instead of 24 bits per pixel or something like that. And then also another thing is the SDRAM bandwidth is used for any other uses of the SDRAM. So if you can, maybe you want to execute some code from flash or internal SRAM, so that way it's not using bandwidth that is used by the external SDRAM. But there's actually a way that you can configure the part to give the highest priority to LCD, so it won't matter if you use the SDRAM for other things. So, and that is with the 1788 LCD AHB Priority Arbitration Register. So this register, what this allows you to do is it allows you to program which system devices have the highest priority on the AHB bus. To give the highest priority LCD DMA, you can use this value here. So this ensures that if you have tearing on your LCD, that it's not caused because you're executing code out of SDRAM. It's just so. But this is actually a really good idea to have this set, regardless of any other thing you might see in your system. So now let me talk a little bit about some of the software and tools that are available to make using the LCD controller easier. Because, I mean, I described the LCD controller, and I'll tell you honestly, it's not really that hard to set up. And once you have it set up, it just shows stuff on the display. The tricky part is to actually render what is going to be shown on the display, because it's hard to make things that look, good. People have good expectations from smartphones and PCs, and so you need to get a graphics library, because it usually can take a long time just to even be able to render a window on the display and have it look good. So the basic thing, the most basic library that is available is Swim, which is free. So this is actually from NXP, and we developed this to help people start out. It's got a few fonts in it, so it can render text. There's some text there. And it draws boxes, lines, and it sets colors. So this is a pretty elementary graphics library, which I can definitely say that now that we offer EMWin, you probably want to look at EMWin before you look at Swim. But this has been available for a long time, and it's free. So if you're trying to bring an LCD up, if you have like a brand new board and a brand new LCD and you want to bring it up from scratch, here's how to set up Swim. There's actually a structure inside of LCD params.c where you put in the resolution of the display and the bits per pixel, and you put in the vertical back porch and the vertical front porch, all these different things from the LCD datasheet. And then there's some code in Swim that sets up the power for the LCD controller and opens the LCD and sets it up for you. So this is a good way to test an LCD out of the box, because it's just really simple code. Another thing that's available that comes with Swim is LPC bitmap converter. So this is something that this will create it'll take a bitmap and make a C structure for you. But what it doesn't do is it doesn't implement any kind of compression. So it'll take up a lot of storage. But it's a very simple way to get started if you want to display a bitmap on the display. So here's some hardware that you can also use to get started with some of our parts that support LCD. One of them is the Embedded Artist 1788. This is actually called the OEM baseboard and the 1788 OEM board. The reason why they call it that is that they sell this module separately with the 1788 on it. But if you get this module and this baseboard, they also have displays that plug into here. And you can see this at our booth. We've got this set up with a display. But in addition to this board, evaluation board, there's also the IAR Kickstart for 1788, which is, we have that in the booth too. It's really nice. It looks like a metal control panel like you'd see in a factory. It's like kind of ruggedized looking. It's not your usual eval board. But then there's also FDI. FDI makes a really nice board. They have a 7-inch LCD. Then on the back of it, there's a 1788. And it definitely would look nice mounted on something, because all the circuitry is on the back, so it doesn't take up any extra room around the display.
They sell that as a module as well.
Yes. So I guess everybody's selling these things as modules. If you want to design your own board, probably you could start to talk to these people and you can get their schematics and everything, or you could just buy modules from them. For IDEs, there's the LPCXpresso IDE. This works with the 1788 and NXP's other Cortex products. LPCXpresso is free, supports up to 128K of code. And you can just download it from our website. In addition to LPCXpresso, there's Kyle Microvision. This is a really popular development environment. There's the Code Red Red Suite. Code Red Red Suite and LPCXpresso are somewhat similar. They're both Eclipse-based and GCC-based tool environments. But the debugger is much, much better than what you would normally get with a GCC, like a GDB-based tool. So that's definitely something. You shouldn't confuse LPCXpresso free with, like, off-the-shelf GDB. It's much improved over that. There's also the IAR Embedded Workbench. IAR is also the vendor from which we license the EMWin library from. And then for JTAG debuggers, pretty much any debugger that supports a Cortex-M3 will work. So that's from the LPC link to the red probe to the Kyle U-Link 2 to the J-Link. Those will all work. If you need more information on LCD, we have actually we have a peripheral driver library. Sorry, this is other support material that can help you get started. We have a driver library for the 1788. This is available. So these links are actually old, but they still work. But we've started to move a lot of our content over to the LPCware.com website. So, and this is available on LPCware. In addition, on NXP's website, there's other kind of techie stuff, like there's BSDL files if you want to be able to test your board when you're done manufacturing it. We have IBIS models, which also help you to simulate the memory interface if you want, and ORCAD symbols. We have an app note on how to implement touchscreen. So touchscreen is actually really, really simple to do, a 4-wire touchscreen. You can do this just basically with the on-chip A to D and 2 GPIO pins. So we have an app note on how to take care of that. And then also the LPC3250, the ARM9 product, that actually has a dedicated hardware device to monitor the touchscreen. Although with the 4-wire touchscreen, it's really not totally necessary. So. We also have an example that shows how to configure the LCD controller for a bunch of different panels. And this is for the LPC247X. But this same example applies to the 1788 because we use the same LCD controller. And then finally, onto packages, LCD drawing packages. One package that's pretty cool is Blue Water Embedded Prism Micro. This is kind of a low-cost package. It's designed to do palletized 8-bit color. But they also have a higher-end package, regular Prism, which will do more colorful graphics. The FDI Micro Easy GUI, this is what we have in the booth. We have one of these. This is actually a 7-inch display, so that's actually a pretty large display to see. It's WVGA 800 by 480. Seger EM1, this is our free library, which you can see at the booth. There's evaluation versions you can download today, and then the full development version should be going up soon. One thing is another third-party offering that's kind of interesting is I2ST. So I2ST includes a Java virtual machine. So they've actually ported onto the 1788 a Java virtual machine. So if you're developing code in Java, that would be a really good thing to look at, not because it has a cool GUI, but because it's a Java virtual machine. But it also has a cool GUI. We have this at our booth. You can see it. And then there's also a port of the Microchip.NET Micro framework. So here's a number of websites that are useful. I'm going to go through these pretty quickly. But this is one, we're going to start to really focus on this one in the future, lpcware.com. So you're going to see a lot of stuff move over there that used to be on like ics.nxp.com and other websites. And we also post videos online. So generally, anytime you hear that we've given a class, we'll have a video of it online that you can download or play online.